Good Friday morning, everybody. I believe we are on day 726 of the quarantine, or at least it feels that way. If you didn't get outside yesterday and try to enjoy a little bit of the sunshine, then really try to do that today. I got out yesterday afternoon after I did all my classes and stuff and kind of just enjoyed swinging in the hammock for a little while. So it did me some good. Again, I really do hope everybody's doing well. I know that a lot of you had an anatomy test yesterday, and I hope that went well. I didn't hear from a lot of you throughout the day yesterday, so I don't think that stats was on anybody's mind too much as Thursday went on. But we have a new set of notes today. We're looking at the mean and standard deviation of the sample mean. And this, again, is still another relatively easy area to cover. Tylen did request that I do a video on one of the problems for 2.9, and I'll be doing that shortly and getting that out as well. So right now, let's just go ahead and we'll jump in to the mean and standard deviation of a sample mean. The first part of calculating the mean of a sample mean is kind of redundant, but we're going to go through the exercise anyway just to show you why it works out the way that it does. I'm going to give you a little spoiler. The sample mean is equal to the population mean. If it's not, then there has been an error computed somewhere along the line. With the first example, we're going to come up with the let me highlight this so you can see that what I just said was that the sample mean, mu sub x bar, is equal to the population mean, which is just mu. So we're going to refer back to our basketball players that we had on the last set of notes. They may even have appeared in the notes before that too. But we're talking about their heights. We want to determine the population mean. So fortunately, we've already done that in previous examples. So I'm going to pull up Google Sheets and show you the population mean is highlighted right down here. It is 80. We just took all of the individual heights of the 5 basketball players, added them together, divide by 5. You get the population mean. Well, part B wants you to obtain the mean, mu sub x bar, for the variable x for the sample size of 2. Verify that the relation mu sub x bar is equal to mu holds. What that's asking us to do is to take every conceivable sample size of 2, which we did in the previous set of notes, and so we're going to reuse that here. And we find the mean of each one of those individual samples, and then we take the mean of all of those means. It sounds like a lot of means going on. But let's pull this up. So right here in blue is the sample mean for each one of these sample sizes of size 2. I need to flip my keyboard out here. If we want to calculate the sample mean or the mean of the sample mean, it's just simply in Google Sheets, it's equal to the average of all of these values. And we do in fact get 80. Part C asks you to repeat the same process for sample sizes of size 4. And again, I'm reusing the step that we have done in the previous set of notes. We already computed the sample sizes of 4. We found each one of their individual means, and now we want to come up with the sample mean, or the mean of the sample mean. So again, it's average. If I can type. We're going to highlight all of those sample means, and we get 80. So in both cases, what we were looking for was what is the sample mean, the mean of the sample mean for sample sizes of 2, sample sizes of 4, and so on. So that's all you got to do. You're just recalculating a new mean. Your sample means should be equivalent to the population mean. If it's not, we need to go back and reevaluate things. So nothing real fancy there. Just know that the sample mean, or the mean of the sample mean, is equivalent to the population mean. That's the big thing that we wanted you to take away from that. The standard deviation, it's not going to be a difficult computation. We're not introducing any new mathematics here. We're still using the same formulas that we've used before. So for part A, it says determine the population standard deviation sigma. So with the population standard deviation, let's see, I think I may have already calculated it. I did, but I didn't show how. So let me go back. All right, so let's look at part A. So for part A, the sample or the population standard deviation, the formula, if you recall, is the sum of the data points minus the mean quantity squared over the size of the population. So it's the square root of that whole value. So for part B, or for part A rather, we're still working on that. If I substitute in everything that we know, we start off with player 1, who is 76 inches tall, minus the mean quantity squared, plus player 2, who is 78 inches tall. Go on to player 3, player 4. I'm going to run out of room, I'm afraid. And then player 5. And then we divide that by the size of our population, which is not n, it is 5. And we type that in the calculator, and we get sigma is 3.41 inches. So there is our standard deviation of the population. Now we want to obtain the standard deviation of samples of size 2. So I'm going to go back to Google Sheets, and this time I'm going to use Google Sheets to do the computation for us. So we will go right here, and in this, I'm going to add a column in here. I didn't give myself enough room. Okay, so I'm going to square the sample mean. So right here I may just say x squared, or sorry. How do I want to do that? Yeah, we're going to say x minus, I'm going to say mu squared. So what we're doing is it's going to be equals this value. Let's see, I should put that in parentheses. This value minus our mean, which is 80, quantity squared. And you can see we get 9. We can drag this down, and it does the computation for each one of these. So it takes each one of the sample means, subtracts 80 from it, and then squares it. And the next thing we need to do is get the sum of those values. We get 43.5. One final step. So let me just give this a title here, standard deviation. This is going to be equal to the square root of the sum of all the x minus mu quantity squareds divided by our sample size, which happens to be 1, 2, 3, 4, 5. It's going to be 10. So we type that in, and we get 2.09. So for part B, we can say that the standard deviation for samples of size 2 is 2.09. Clear this off. Inches, got to be specific. And then it says repeat part B for samples of size 1, 3, 4, and 5. Well, rather than walk through that same step process over and over and over again, I've already calculated those right here. We have sample size 1, which we did using just the manual calculation and the calculator at the end, we did come up with 3.41. Samples of size 2 is 2.09, which we just calculated using Google Sheets. And then 3, 4, and 5 I went ahead and calculated, and we get 1.39, 0.85, and 0. Your last value should always be 0 if you have a small sample, because if you can test your entire population, then your standard deviation should in fact be 0 for the for the mean of the sample mean, or for the standard deviation of the sample mean, sorry. So just, if you need to, just go back and watch the steps one more time on how we calculate it using Google Sheets. We've done this before, so this isn't new. We're just getting more practice with it. Then I believe we actually only have one more example. We're going to put it into practice. Here are the formulas that we've used. So if there is no sampling, if sampling is done without replacement, you would use this formula. If sampling is done with replacement and it's a finite population, then you would use this formula. And this is typically the one that we're going to use most often. The sigma x bar is equal, or sigma sub x bar is equal to sigma over the square root of n. That is one way to show the standard deviation of a sample set. So we've, right here you can see where it says applying the formulas, we've shown that the sample formulas relate to the mean and standard deviation of x bar to the mean of the mean and standard deviation of the population. Namely, mu sub x bar is equal to mu, so the mean of the sample mean is equal to the mean of the population. And then sigma sub x bar is equal to the standard deviation of the population divided by the square root of n, where n is your sample size. And we're going to use that here in example 3. So for example 3, we have the U.S. Census Bureau in current housing reports. The mean living space for single-family detached homes is 1,742 square feet. Assume a standard deviation of 568 square feet. For Part A, samples of 25 single-family detached homes determine the mean and standard deviation of the variable x bar. For Part A, mu sub x bar is easy. Mu sub x bar is equal to the population mean, which we already know to be 1,742 square feet. So no calculation to do there. It was already done for us. We know what the mean is. For the standard deviation, so now we're looking at sigma sub x bar. We're going to use that formula that was listed earlier, where it's sigma over the square root of n. And in the case of our example here, we have sigma is 568 over the square root of 25. That's our sample size. And when we type that into our calculator, we get 113.6. Again, that's square feet. And then for Part B, which somehow I've managed to label with a bullet instead of calling it Part B, it says repeat Part A for a sample size of 500. Well, we don't need to repeat the mean of the sample mean because we already know it's 742 square feet. The only thing we have to recalculate is sigma of x bar. And we're going to have, again, I'll just write it down here, sigma over n is equal to 568 over the square root of 500. Again, type that in our calculator, and we get 25.4 square feet. So what that just tells us is for Part A, samples of 25 single-family detached homes, the mean and standard deviation of all possible sample mean living spaces is 1,742 square feet, and then the standard deviation is 113.6 square feet. And then as we take a larger sample, we notice that our standard deviation actually gets smaller. We look at 568 over the square root of 500, we get 25.4. Again, the mean is still the same as the population. So that is going to be it. Now we're going to start building onto this, and we're going to start looking at more of the sample size and sampling error. But some of the key points that you can see are highlighted right here in these 3 bullet points. The larger the sample size, the smaller the standard deviation of X bar. The smaller the standard deviation X bar, the more closely the possible values of X bar cluster around the mean. And the mean of your sample means is equal to the population mean. So this kind of gives you a feel for where we're going. And like I said, we're going to build on that 2.11. We're going to start looking at some more of the math behind all of this. But I hope that this makes sense. I do still hope that all of you are doing very well. I will probably be seeing you guys in about an hour and 45 minutes for our Friday Zoom class. I'm looking forward to seeing you guys. I hope you guys are just having a wonderful day, and I really do miss seeing all of you. Jaron, if you're watching this, I hope yesterday was awesome, that you had a great birthday, and that's it. You guys take care.